Hello again, folks. Today we're going to be covering section 8.2. I'm going to have to modify the schedule just ever so slightly. Here's a quick view of the calendar. It was supposed to cover 8.1 and 8.2 yesterday, of course, but I decided to just do 8.1 on Monday. This video is for Tuesday, and I'm going to just cover section 8.2. So that means I'm going to boot 8.3 to Wednesday, and I'll do 5.1, oh pardon me, I'm reading it backwards, 9.1 on Thursday. I would prefer not to mix 9.1 and 9.5, but I'll look at it at that point. All right. I may end up taking advantage of my little buffer day that I have worked into the schedule. Anyhow, everything will get covered in time, but I'm going to do section 8.2 just for today, Tuesday, June 21st. Okay. Having said that, the packet that I have for you is a bunch of different pages, including this one. This is an older diagram, some of the same information I have elsewhere in the packet. What I really want when I get to it is to just focus on the bottom here. This is a worksheet. We'll be in person. I would just go through a couple of these with you to demonstrate the outcome of generating your own coordinates. This is some graph paper that I have rigged up for specifically demonstrating tangent graph, cotangent, secant, and cosecant. The increments here are spaced 4 blocks, and they're in fractions of pi, as you can see. And this is the information that I swiped from your textbook because I felt it was a better summary than anything I could give you. So that's as concise a bunch of information about tangent and cotangent and secant and cosecant respectively. And so anything that you would be interested in would be in there. Okay? Alright, so if you're following along, just print this out. I'm going to give you some info for this. Okay. Dropping something here. Maybe I should put my glasses on. Good idea. Okay. Let me turn on my projector and adjust the lights. As always. Okay. Bear with me. It always takes 2 clicks. Let's see if I can get away with just doing this. No, I think there's too much of a glare always. So I will improvise. Alright. That's annoying. Alright, you know what? I'm kind of spoiling. Yeah, let me do this first. Just a quick little reminder of what's forthcoming. Right, last class was section 8.1, naturally, and we covered sine and cosine graphs. 8.2 is the other 4 of the 6 trigonometric or periodic functions. Right, periodic meaning that these things repeat indefinitely. All right. Section 8.3, which I'm going to reserve for tomorrow, this is about inverses. And anyhow, we are dealing with what is in red here today. And to help encapsulate that information, I made this little worksheet. Oh, green, go away. Alright, so if you see this page in the documents, just if you would scroll to the bottom, and I'll try to summarize. Okay. Alright. A little bit of information before we get to the actual graphs. I may need a little bit of light. Okay, that looks like it's alright. Just a review of sine and cosine firstly. All right. What would be good to know insofar as sine is concerned, and then cosine. Sine is basically a circle unraveled. I think that is a good way to think about it. All right. Over 2 pi, at least under normal conditions. All right. And cosine is basically just the same waveform, all right? Meaning it is sine. It's a sine wave. Sinusoidal is what you would say. Out of phase. All right, by 90 degrees, or you could say pi over 2. All right. I think that is the best way to think of both of these things, because if you know that, and you have the basic gist of how a sine would work, all right, how that would look, you could just shift everything over by 90 degrees, and then you have a cosine. All right. The new stuff that is, quasi-new, somewhat new, tangent, cotangent, secant, and cosecant, which again I would memorize in that order, is based upon, firstly, the ratio of these two things. So tangent is essentially the ratio of sine of x over cosine of x. All right. And cotangent, which is the cofunction naturally of tangent, is the reciprocal of tangent. But also out of phase by 90 degrees, pi over 2. That is the nature of the cofunctions, remember. The cofunction of sine is cosine, it's out of phase by 90 degrees. All right? Tangent is the reciprocal of tangent. It's not going to look exactly like it. It kind of looks like the mirror image of it, basically, you'll see. But it is also out of phase because it's a cofunction by 90 degrees, right? Then there's naturally secant, and cosecant. I'll put these in different colors. Right? Secant is, remember, the reciprocal of cosine. Right? Which means that it would look like this. It would be 1 over cosine, that is the equivalent. All right. And cosecant, being that it is the cofunction, would be out of phase with that, but let me, actually, I'm jumping the gun a little bit. Cosecant is, remember, the reciprocal of sine, which means that, hopefully my cup is not in the way, it would look like if you were going to use your calculator, say, to draw it, right? 1 over the sine of x, right? And way out of phase with secant by pi over 2, so 90. Right. Once again, if secant is the reciprocal of cosine, all right, and cosecant is its cofunction, it is the reciprocal of sine, cosecant, but it is out of sync, right, out of phase, with secant specifically, right, by 90 degrees, so pi over 2, right? That's a good summary, I believe, to think of these things and how the graphs will evolve. Okay, we're going to start with this. All right, tangent as being that ratio. Now in theory, cotangent, because it is the reciprocal of tangent, there's a couple of different ways you could write that. You could just simply write 1 over tangent, right? Or you could take sine and cosine and reverse them, right? Cosine of x over the sine of x. Okay. Now there are some fun facts up here. Yeah, they're in. I have it elsewhere in the same set of packet. But before we get to tangent, here's some things to bear in mind. I'm gonna erase this now. There is no amplitude in the classic sense of a wave, because the wave doesn't quite look like a sinusoidal wave, right? Remember, the sinusoidal waves, look like this. And they have an amplitude. Tangent waves, you're going to notice they are waves. They're periodic, but they don't quite look like that. So it doesn't have an an amplitude in the classic sense. It has what we would just refer to it as a stretch factor. So it elongates, or in theory could be more squat. All right. What is different about tangent from cosine and sine is the period, especially. Right. The period is really it's just pi, all right? If you have some horizontal stretch or compression factor, then it in theory would be calculated by pi over b then, okay? The domain is affected by what will be essentially asymptotes. So that's why this is summarized as x is not allowed to be such and such conditions. Why? Because those are the locations generalized for what will be asymptotes. All right, so there's a restriction in case of what x is. On the other hand, the range, the y values are negative infinity to positive infinity. Okay, and technically it is an odd function. Okay, if you have a more complex transformation, you might read this instead. All right. Okay. All right, now let me show you this. This is an old worksheet that I used to go through with people. All right, here's the whole thing. It's a little bit of overkill. But it is an example of the brute force way of producing the dots that would make the picture. All right, it's generating your own coordinates. All right, now it's a little bit hard to see up here. I'm not going to do the whole thing, but let me zoom in. If, let's just say that we did, I think, this much of it. At the very tippy top here is our reference, right? A tangent, as I mentioned already, comes from the ratio of sine over cosine. So if you just knew this much, right, the value of a sine wave at those distinct points, 0, pi over 2, pi, 3 pi over 2, and 2 pi. If you know this much information, 1 positive, 1 negative, that at, say, for example, a sine wave at x input of pi over 2 is the value of positive 1, you could, without a calculator, figure out what the tangent would be, right? You would have to compare that naturally to the graphs of a cosine. Using those same points, remember that they're out of phase by 90 degrees, so here's pi over 2 again, pi, 3 pi over 2, and 2 pi, and here's 0. That's positive 1, and -1, and these points. Probably should have done that differently, but hey, different colors. Start goes here, there. It's the same waveform shifted, alright? Let me scoot on up here. I'll move that out of the way. Bear in mind, where the ratio would be over 0, that is, if you have whatever number on top of 0, that is essentially trying to divide by 0 in consideration of that ratio, and that would be regarded as undefined. That is why there are asymptotes on a tangent graph. Anyhow, I'll just do a couple of these brute force here. If I were calculating tangent of x at these points, just a couple of them at least, you'll start to see what they would evaluate to. Right, and how you could figure it out with or without a calculator. Right. As I mentioned last time, it would be good to memorize the values of a sine graph at these respective points and a cosine graph at these respective points, since everything that follows is really contingent upon these two things one way or another. Alright. Here, tangent of x, if it is a sine value of x over the cosine of value of x. Alright. If you input it at 0, and then 0 here, the value of sine at 0 is 0. The value of cosine at 0 is +1. So this is legal. It's 0 divided by 1, which means that overall it's 0. So if you evaluate tangent essentially at 0 using x input of 0, right, the y output would be 0 as well, which is an actual point, the origin, 0, 0. Right. If you did it again, right, using pi over 6, you may remember that this is 60 degrees. Pardon me, that's 30 degrees. It's 180 divided by 6, and this is really 30 degrees. And this would also be 45, and this would be 60, and that would be 90. Right? So you could incorporate special right triangle relationships if you were doing this by hand. I'm not really trying to belabor the point, but it helps to go through the mental exercise, because then you're more likely to remember something. And it makes you more strategic when you remember things. So just say hypothetically that you inputted the tangent of pi over 6, right? That essentially would be sine of 30 degrees and cosine of 30 degrees, right? Which, if you remember special right triangles, they have a relationship between 30 and this would be 60 here. Between 30 and 90 is the value of the square root of 3, right? And special right triangle relationships, the 30, 60, 90 type. Over here would be 1 and this would be 2. Sine of 30, pi over 6 is the same thing, would be opposite of that. Opposite of 30 is 1 over the r value, which would be 2, so a half. So the ratio produced by sine of 30 is 0.5 or a half, all right? Cosine of 30 is adjacent over hypotenuse, so it would be square root of 3 over 2, right? And then in that instance, you'd have a complex fraction, which is a half divided by the square root of 3 over 2, which means I'm just going to put it here and then I'll erase it just for the sake of space. You would end up multiplying by the reciprocal, so 2 over the square root of 3. Keep change flip produces that. There would be a cancellation effect in that event, and then technically you would start with this. You'd have 1 over the square root of 3 which is an example of something that would require, at least for the sake of good etiquette, rationalizing the denominator because of the radical here. It's the same value, but the best explanation I can give you is that nowadays it's just regarded as bad etiquette, but at one point it would be very impractical, without a calculator certainly, to have a radical in the denominator. It just makes things very difficult. So you write an equivalent expression. You rationalize the denominator. How so? Most of the time, it's really just replicating the denominator to produce a ratio of 1. Multiplying by 1 doesn't change the value of something, it just changes its appearance. So what you would end up with is the square root of 3 over 3. That means that the tangent of pi over 6 would be equal to whatever the square root of 3 over 3 is. Right? And therefore, right, the coordinates would be in tandem. At pi over 6, you have the square root of 3 over 3. Now that may not mean a lot, but let's prove with our calculator that that calculation is in fact true. All right. First of all, should probably make sure if you're going to use pi over 6 that your calculator is set to radians. So tangent of pi over 6, all right, should produce the decimal equivalent of square root of 3 over 3, which is really just 1 over the square root of 3, because it comes from special right triangle relationships and this ratio. A fraction over a fraction ends up producing this in red here. Anyhow, the square root of, tangent of pi over 6 is this decimal, 0.577 something. All right, that may not mean much, but what is the square root of 3 divided by 3? All right, it's that decimal. That's why you would get that. All right. Okay. Anyhow, in the case of pi over 4, you could use the special right triangle relationship of 45 degrees. All right. What I'm going to do now is simply give you some of this information rather than reinvent the wheel. All right. And just remind you that this is about 0.577. So if we were to graph this, you would look at the halfway mark and then do a little bit extra. All right, so 0.577. Okay. I'll get rid of this. Okay, so if this were evaluated, tangent of 45 degrees, pi over 4, all right, the result would actually be 1 because of special right triangle relationships. Right? Remember the 45, 45, 90 triangle. Right? In that event, the coordinates that you would pair together at pi over 4 would be 1. That's easy to graph, right? And then if you did pi over 3, which is the equivalent of 60, again using special right triangle relationships, you get this. Technically it would be the square root of 3 over 1, which is the square root of 3. In terms of the decimal, that's about 1.732. All right, and paired together at pi over 6, square root of 3 over 1 is again just about 1.732. One more of these, and then I'll stop. When you get to 90, right, and you attempt to evaluate tangent at 90 degrees, pi over 2, in radian style, what ends up happening is that it's undefined. Let me show you why. right? In this case. It's undefined, which means that there is an asymptote. At pi over pi over 2, there's an asymptote. And there would be elsewhere because it's a periodic function. Right? If again tangent arises from the ratio of sine over cosine, and you have these graphs again to help you evaluate. If you put in pi over 2 here and pi over 2 here, right, don't use a special right triangle in this case, just use your sine wave knowledge. Right? Sine, which is this one here, evaluated at pi over 2 is legitimately positive 1. So up on top you'd have positive 1, no problem there, right? If on the other hand, you went to the cosine wave, right? Maybe I should label this. This is sine, this is cosine. If you went to the input value along the x-axis to pi over 2, 90 degrees, what is the y value of cosine? Right? It's right on the axis, so it's 0. Right? And in that event, you have the situation where you have 1 over 0, which is essentially like dividing by 0, which you can't do. It's a mathematical impossibility. You can divide into 0, you can't divide it by 0. All right. Anyhow, the result is that this would be undefined. If you do this with your calculator, you get an error message, right? Right? It is at that point, at pi over 2 along the x-axis, that the first asymptote would appear, at least in the positive direction. Right? It turns out, and again, you could keep doing this indefinitely, all right, that you will get further, more and more asymptotes. Right? At negative pi over 2, right, you'd have the same thing. I didn't put it here, but if I put negative pi over 2, y of negative pi over 2 would also be undefined. Right? Because there's an asymptote. Since cosine is the denominator, essentially in this ratio, the bottom of it, we have to avoid 0 in that place. Otherwise you go to math hell, right? All right. Anyhow, what I did was I actually drew these ahead of time, and I'll show you the drawing. All right. Hopefully it's not too faint. And then I'll give you a little bit of extra information. This out of the way. Here is the actual graph of tangent were you to plot the points that I just generated from, brute force from that table, right? Basically, although it's not written on the photocopy that I give you, right? If you want to, I did make it available in Canvas. Here's an actual blank if you want to draw this by hand, and you might go, why do I want to do that? Because if you try to draw something, a lot of times it helps you remember things. All right, that was really only my motivation for giving you that. Anyhow, take a look at this. All right, and I'll just point out and highlight some features here. All right, it's a little faint, all right? But as I mentioned, if you look here, the way that I divvied it up, I chopped up it in increments of blocks of 4 here, is 90, 90, 90, 90. All right, pi over 2, another 90 is pi, 180. 3 pi over 2 is 270, and 2 pi is 360. If you want to print out the actual prefabricated version of this, which is also available, I would just highlight these vertical dashes here, because that is the asymptote, right, on that end. And then here's the other one at negative pi over 2. Right? And here's what would happen if you use the points that I had calculated. Right? These aren't perfectly spaced, but they would be in this particular order. What I have written here, and it might be a little bit hard to see, are the inputs of, on this line here, pi over 6, which would be 30 degrees, right? And then what would follow it would be pi over 4, which would be 45. I mean, that much would make sense because it would be halfway to 90. And then the next one would be pi over 3, right, which would be 60 degrees. All right? And over here to those in reverse, negative pi over 6, negative pi over 4, and negative pi over 3. Right? So negative 30, negative 45, negative 60, if you will, negative 90. The points that I had calculated were just the positives, of course, right? But I drew them here, right? Assuming that pi over 6 would be about on this line here for an x value, if you were to then go up to the equivalent, which was 0.577, so a little bit bigger than a half, right? The way that I spaced the vertical axis here, I did 3 increments here, 3 blocks. So halfway would be right about there. The first dot would in theory be just above the half mark, so just about there for pi over 6. And then the one that would be easy would be at pi over 4. You go up to an actual 1, right? And then for pi over 3, it would be 1.7, right? So if you figure that the way that I have it incremented, that this is in thirds here, that would be 1.333 repeating, 1.666 repeating, 1.7 would be just above this line, right? So for the pi over 3 x value input, you'd have a dot roughly here, right? If you were to calculate the negative incarnations of these, all right, it ends up like this. I'm going to get this out of the way because I think it's blocking. At negative pi over 6, it's still 0.577. So if you figure again, halfway from 1 to 0 is a half, 0.5. 0.6 would be just under that, right? And then at negative 45 degrees, or negative pi over 4, you'd be actually at negative 1. And then at negative pi over 3, 60 degrees, all right, you'd be at 1.7 again, or in this case it would be negative 1.7. So you have a dot like that, right? And basically this is why it's not sinusoidal. It produces a wave, but the wave looks something like this. It's a little bit squeaky. And it would approach this value of 90, all right, but never quite reach it, right? On both sides, right? Now, because it is periodic, what you should expect is that this repeats. So, if you were to do the calculation for the points that would be in here and in here, you'd have the same curve, right? It is very similar to the cubic graph, y equals x to the third, right? But it's actually tangent, right? So probably not exactly the same, just superficially similar, right? If you went back this way, you would see through negative pi this wave like so, right? And like that. And building up from here. Right. If you wanted to calculate the other asymptotes, I'm stealing this from the information that was provided by the book. It would be pi over 2 plus essentially a multiple of pi. So if you had pi, right, times 1, right, you'd get from added to 90, you'd get to here, right? So that's why there's another dashed line like this, because this is yet another asymptote. And then there would be another one back here if you use negative 1 times pi, all right? And perhaps most interestingly of all right, notice the period, all right? The period for the one complete wave cycle, and this is, you know, not sinusoidal, mind you, would be really just pi. It's just that it doesn't start at 0, right? All right, it's a half plus a half, so it's pi the whole way. Okay, that's kind of neat, right? Anyhow, let me show you the other ones. Right. Being that cotangent is the reciprocal of tangent, it would look like this. It's a little bit faint because of I scanned this with my printer. Let's point out, maybe highlight some key features here. Right? Because the cotangent of x is the reciprocal of tangent, it's just out of phase, it's a cofunction by 90 degrees, the asymptotes themselves and everything would shift, right? Also, the basic shape of this more or less looks like the mirror image of tangents, right? Sound effects not necessary, I know, but I can't help it. Right. Anyhow, so you see that, again, for lack of a better phrase, non-sinusoidal kind of wave. It's this, goes through pi, negative pi over 2, and curves like that instead. Okay. Kind of the reverse staying alive gesture, you know, from disco days. Right? You have that. Okay. Looks very similar to tangent naturally. All right. Being that it is the reciprocal, but it is more or less in reverse, if you can think of it that way. All right. Where I put this is alluded to this over here. Where tangent would be increasing, essentially cotangent would be decreasing. All right. Nonetheless, the period, the space between, you know, one complete wave cycle, or between the asymptotes if you prefer, is still a half plus a half. So the period is still pi. Right? If you were using your calculator to draw something like this, then you could just input it like this, because we have a button that says tangent on our calculator, so you can just put 1 over tangent of x, and that's sufficient. Okay. Here is secant. Right. This one's kind of fun to craft from scratch, right, given its relationship to cosine. Right? Because secant is the reciprocal of cosine. If you were going to, the old days when they used to make us do this by hand, they would say, draw a cosine, right? So if you haven't memorized, right, using the same graph paper, that the points of interest, at least to produce a cosine, a very basic one, from 0 to 2 pi, would be points of 0, 90, 180, 270, and 360. And that for cosine in particular, it's out of phase with sine. So instead of being at 0, 0, it's at 0, 1, right? And then it curves down to 90 and is 0 at that point. And then, because I have it incremented down to here, it's negative 1. There would be a dot here. And then it would arc back up to 270, and then curve up to here to 1 again at 360. All right? The rest of the wave would be like this, right? At least if I was to go backward. That's cosine, all right? Again, why am I mentioning this? Well, because secant is dependent upon cosine, because secant of x is the reciprocal of cosine. Right? The way it works out is that you would again have that situation where you would have asymptotes, right? Points that are basically domain restriction. Things that x values are not allowed. So I'm just going to highlight those asymptotes here, here, and here. And the actual graph that would be, I'll put it in black, the secant graph, I have it in green on my copy, would be sort of a U shape. I think I made it a little bit too like a parabola. It should be a little bit flatter, you know. It would be at what would be the peak of this amplitude of the cosine. And that's the reason why this is only dashed, because it's just for construction purposes. And it is a periodic function as well, so it would cease to exist basically at the asymptotes, but it would be inverted like this, right? In this range, right? Well, this domain, technically speaking. Okay. And again, it would pick up over here, and it would repeat because it's a periodic function, like so. Make it a little bit more U-shaped than V-shaped. Okay. Again, the blue cosine wave is really not the actual secant. That's just what you use to draw the picture. Right? They're construction lines. Right? The period, in this case, right, be mindful, is not just one of these sort of curves. It's two of them, but one upright like a tulip blooming, and one like a tulip wilting. All right. So for that reason, the period is really 2 pi again. Right. It really needs to have what would be regarded as the periodic wave would be this and that, not just one or the other. Okay. So 2 pi. All right. A half and a half is 1 pi, and then another 2 halves is 2 pi. All right. That's secant, one more of these. Here's cosecant. Yeah. All right. It's a very similar graph, naturally. But just to point out and highlight some information, being that cosecant is the reciprocal of sine instead, all right? If you were going to get your calculator to draw this for you, remember you could just opt for, writing it in its reciprocal incarnation here. Sine of 1 over the sine of x, all right? And it would produce this, all right? It has asymptotes where sine would be 0, all right? Okay, so here's the asymptotes again, these dashed lines, just to emphasize. You could, if you wanted to, again, and I was decidedly more faint when I did it this time. The sine would be like this normally, right? I'll put it in red because it's just a construction line, a construction curve, I guess you can say. Right. The actual graph, that is the cosecant, would be similarly these sort of U shapes, all right? But they would be riding on the peaks of each of these, or the valleys, if you like. And do try to make these a little bit more U-shaped than I did when I originally drew this. Okay. All right. The period is, once again, not just one of these curves, but one version of it upright and one of it pointing downward. So one blooming and one wilting, if you will. All right. Period is still in 2 pi, right, to get a complete wave, if you will, non-sinusoidal, if you will. Okay. All right. All right. Let me leave it at that. I figured that is enough information to assimilate, alright, without involving the inverses. Alright, so I'm going to do inverses tomorrow. Alright, again, this video is for Tuesday. 8-3 I'll cover on Wednesday, so I'll see you tomorrow. Alright, be careful out there.